Section 9.3, Measures of Regression and Prediction Intervals. As you can see in our previous two sections, with the correlation, we can see where the directionality is. We can predict the line with regression, but as you see with regression, it's not on a perfect line. There is going to be a range above or below it. How accurate is that? And that's really what we're going to be doing today, is learn what is the range going to be. We can look at the correlation coefficient to determine how close it is. A lot can be explained, but some cannot be, such as we're looking at Old Faithful. It looked like a very strong correlation, and the line was real close to it for eruption times as well as times between eruptions. But it's not 100% perfect. And when we look at this, we can determine how accurate it is by looking at the explained variation over the total variation. This is the coefficient of determination. If the coefficient correlation is 0.9, then the coefficient of determination is 0.9 squared. It's the R squared, be 0.81. And what this really is saying is 81% of the variation can be explained between the X and the Y relation, which means 19% it cannot be explained. For example, we know how to find R. We found that with our little calculator before. And this is the equation. We did this in 9.1. We got an R of 0.874. And this is for GDP, gross domestic product, of 10 countries and their CO2 emissions in terms of metric tons. We found our R. And our R squared, 0.874 squared, is 0.764. So in other words, the relationship between the gross domestic product and the CO2 emissions can be attributed to 0.764, 76.4% of the time. It can be explained between these two sets of data, which means that 23.6% cannot be explained. There'd be other things. What would it be? Perhaps there's laws in some countries. Perhaps they're using different kinds of fuels at a higher rate than average. But what we're saying is we can predict 76.4%. That justifies that. The other effects beyond the X and the Y are due to 23.6%. And I'm talking about Old Faithful. We had an R of 0.979, so almost a perfect line as we saw in 9.2 with the regression line. But it's not 100%. My R was 0.979, which we figured out in 9.1. I squared that, I get 0.958. 95.8% of the variation can be explained between the relationship between how long Old Faithful erupts and versus time between eruptions. What are other things? Well, we don't know, and that's what we need to look at when we're studying this. It could be rainfalls. It could be glacier melts, because that is in the Rocky Mountains where that water is fed underground. Who knows what it could be there? I think there was an earthquake there about 20 years ago, and it slowed down the time. It may have widened the chasm underground. I don't know. But we can't explain 100% of the variation because there is some slight variation. 95.8% though of the variation can be explained between the duration and the time. Now, to determine this, I want to show you some things here. We can look at the standard error for GDP versus carbon dioxide as before. There's one of two ways of looking at it. We can either find the slope, and the standard error is this equation right here. Standard error is the square root of sum of y squared minus b, which we found before, times sum of y minus slope, m, times xy squared over n minus 2. And when we do all this, and there were 10 countries, so when we do this standard error, we subtract 2 for the degrees of freedom, so it'd be 8. That ends up being 141.392. We can also find the error by looking at the difference between the individual y's. And what I did the difference between the actual regression and the projection, you see I do a calculation right here. And I'm not expecting to show you there's another way. The difference between actual regression what we projected, and what it was. In other words, if we project it with the equation, it should be along a straight line. Let's suppose we project it right here, but the actual is right here, maybe a little graph here. Or we project another one to be here, it's actually right here. We find those differences are and square them, and that's this answer right here, and we sum it all up. And you can see I get 161,165, which still gives me is 3/10,000ths off, 141.935. So either way works. But what we're looking at basically is the error between what's projected and what the actual result is based on the data we have. And we're going to figure out what variation do we have. Now, I like going with this methodology. And again, because we have all the data right here. This is what I've got here and some time from my own past. Radio time per week. Let's say how minutes per week. Each commercial on a radio commercial is 15 to 30 seconds. That'd be 50 minutes, 20 minutes, 20 minutes, 30 minutes. We've got 8 sets of data here. So, and then weekly sales and thousands of dollars. So the more you can see roughly, the more radio time they have, the more sales they make. And I've done my calculation with a calculator. Found my slope. I found my y-intercept. That's the equation. And then just plug it in. And by the way, I do have a calculator for you for this also. I'll show you in a minute. When I do my calculations, I get a variation of 6.73. So somewhere, no matter what I predict, my forecast, it's going to be plus or minus 6.73. Now, this was our GDP again, with our CO2 emissions. We're using this example quite a bit. And when I do my calculation, if you remember, I get 199.5346x plus 56.036. Now, when I do this, I set up a constant interval. Remember, we're using the t-table again because we don't have a population deviation. So what we're going to do, we have 10 samples. We subtract 2. It's 8 degrees of freedom. So when I do this, here's my y for the GDP. Here is my, here's my slope, 199. And then here's my y-intercept. And I plug these in. Remember, I calculate this out. And what I have here is I have the standard error. The standard error is, as we've shown before, 161,165.1 divided by 10, which is samples minus 2 is 8 degrees of freedom. Now I got this before a couple slides going, 41.135. I got to find my x bar, which is the number of samples of x combined. This is my x average, times 2.28. Now, I plug this all into this equation here. And it's a little messy, but like I said, I have a calculator. Most importantly, I want to find how I found my degrees of freedom. Remember, there are 10 samples, so it's 8 degrees of freedom, as I got right here. It's two-tailed because I'm looking at plus or minus. And it is a 90% confidence interval. You can see the 90% down here, or 0.102 tailed as I have right here. And that gives me a t-critical of 1.860, which is where I got this number. When I calculate this out, my standard error is 281.81. So really what we're looking at here is my endpoints. Remember, I had an average of 614.734 when I was looking at 2.8 for an x. When I put in 2.8 for x, it'd be 614.734 minus 281.81, which is 332.924. And then I put in 2.8 for x plus this is 614.734 plus 281.81, which is 896. So those are my endpoints. So it somewhere will fall when I predict this for 2.8. to be between 332.924 and 896.544. So when I'm looking at this here, we've got basically what we were doing in chapters 4 and 5 with the find confidence intervals. If I put in an x at 2.8 and I want 90% confidence, it's going to fall anywhere between, for my regression line, between 332 and 896. Now, let's use our same GDP data. We've already got our equation, our regression equation. I want to look at $4 trillion for GDP and see what the output for CO2 would be. We've got our equation already, right here, 199.565346x times 4 plus my y-intercept 56.036, which gives me a regression prediction of 854.1744. But what is the range for that? And I want 95% confidence interval this time. Now there's 10 countries, so there'd be 10 is the n minus 2 is 8 degrees of freedom. So when I find my standard error, as before, I got 141.935. My x bar is 2.28. And I plugged this all in as before. The only difference this time is I want a 95% confidence interval. And 95% confidence interval is 0.05 for two tails, I'm showing right here. And here's the 95% confidence. You can see in the very bottom here, guys, it's 95%. And then it's 8 degrees of freedom, so it's 2.306. That's my key critical. And I plug that all in, I get an error, an E of 376.727. So I'm going to do 854.1744 down here. That is the number I'm looking at, plus and minus 376.726, giving me a range of between 477.447 and to 1230.901. So we've got the calculator here, and I've set it up so we can do the prediction intervals. This is my baseball teams. There's 30 of them. All you have to do is put in the numbers, as I've done here, which again, remember, is the total salaries for each team on the X, and then the Y is the attendance. You put in your input, which is number 30 in this case. And 9.3, I've got it at the bottom of the calculator sheet. You can see it. We figure out the R squared, gives you the standard error. And then if I put in the salaries of $200 million, 200 here, and I use my T-table 1.86, it gives me the range of what the attendance would be. At the left endpoint, it gives me an error of 9282.821. It'd be between 12,322 at the lower end and 30,888 at the upper end. And that's all you do. Make sure you put in your data and a 9 and your number of your number of samples you hear. And then basically you just have to put in what number you're looking at, as I pointed out before, there's another arrow, and what your T will be. Looking at the table, remember, and your degrees of freedom when doing this for the error with regression is going to be number of samples minus 2, because you're looking at two different sets of data.